Hi there, and welcome to our lecture on gravity. This is Forces 2 of Unit 6. Key ideas: how are weight and mass related? Why do objects fall to the ground when they are dropped? What's the relationship between free fall, acceleration, and mass? And why do projectiles follow a curved path? Alright, to start off with, how are weight and mass related? Weight is equal to mass times free fall acceleration. So we can define that as, we can define weight as a measure of the gravitational force that's exerted on an object, which can be shown mathematically by just taking, weight is equal to how much mass an object or how much mass you have, and then times the force of gravity pulling down or pushing down on that object. So we measure weight in newtons, so this is the metric measurement for weight. So weight is also related to force. So let's look back at this equation here. Weight equals mass times the free fall acceleration. Well, we just changed F to W. Mass is still M. We changed A to G, so basically we're just looking at Newton's second law again when we're dealing with the weight of an object. So that's why we still use newtons to measure the weight of an object. And weight is different from mass. Mass is the measure of how much matter is in an object, whereas weight depends on the gravitational force that an object experiences because of how much mass it has. A related unit here in the US, instead of newtons we use pounds. So just so you have a relationship there, this is what we're talking about. We're talking about pounds and when it's measured in newtons. We've got something else called the law of universal gravitation. So why do objects fall to the ground when they're dropped? So all objects in the universe attract each other through this force called gravity. And we've got something called Newton's law of universal gravitation. So this gives us the size of gravitational force between two objects. So F is just force. And here I've got the information. G is a constant, so we either have to be given constant or we have to be given everything else to solve for the constant. And then M1 and M2 are just the masses of two different objects. M1 would be one object, M2 would be a second object. And then how much distance. So not only do we have the mass of those two objects attracted to each other, but then what's the distance between? So D is distance between those two objects. And if you notice, the distance is squared. So if we ever square a number, that makes D get bigger faster. So the more distance we have between two objects, actually the less our gravitational force will be. So there's very large dependence on how much distance is between two objects. But then we'll see also that larger objects are obviously going to make this force value a lot bigger too. So all matter is affected by gravity. So two objects, whether large or small, always have a gravitational force between them. And then when something is very large like the Earth, the force is easy to detect. Another quick note on that. We notice a gravitational force when we jump up or we drop our book on the floor, or the book goes crashing to the floor. And that's because the gravitational force of this Earth is huge, it's large, so it's going to have a greater effect on smaller objects like the book. What we didn't say here is actually the book does have gravitational force on the Earth as well. So the Earth is attracted to that book as well, but because the mass of the book is so much smaller, it's not going to be detected that the Earth is actually pulled to that book or slightly. So we're going to say the gravitational force increases as mass increases, and then gravitational force decreases as distance increases. And I mentioned this before when we were looking at the equation. So looking at some visuals here, we've got object 1 and object 2, which happen to be the same mass, so we use just the letter M. So we're going to say that these have small masses. The gravitational force represented by our blue arrows is very weak, so we don't draw those arrows as long. When we've got a greater gravitational attraction or gravitational force, we're going to draw those arrows a little bit longer to show that there's more attraction because we doubled the size of one of our objects. So we kept one the same, but we doubled the size of the other. So even though we didn't change one, we still have that gravitational force of attraction between the two. And then from our first example to the second example, we kept our distance the same. But if we go from the first to the third here, we've doubled the distance. Notice that we just barely draw an arrow, because when we move these two objects farther apart, they're going to be less likely to attract, less likely to interact with each other. So because we increase that distance, that gravitational attraction or gravitational relationship drops off pretty fast. All right, so free fall, what's the relationship between free fall acceleration and mass? So in the absence of air resistance, a lot of times we ignore air resistance in physics to make the math work out a little bit better, a little bit easier, because conceptually we can ignore air resistance and still get an idea of what's going on. So all objects falling near Earth's surface are going to accelerate at the same rate regardless of their mass. So mass is not dependent on this acceleration. So in free fall, the motion of a body, when only the force of gravity is acting on the body, is what we call free fall. So it's just gravity pulling us towards the Earth. We're in free fall, and we're going to ignore air resistance, even though it's always present. Air resistance can balance out the weight of an object. So again, weight is the mass times the acceleration due to gravity. In order to balance it out, though, we have to have something that increases the air resistance considerably, because that force of gravity is pulling us down at such a great acceleration. So maybe we have a parachute to equal out those, or to relatively equal out those forces. We're still going to come down towards the Earth, and actually the parachute will stop the acceleration, so we're just dealing with velocity then. Terminal velocity, it's the constant velocity of a falling object when the force of air resistance is equal in magnitude and opposite in direction to the force of gravity. So if we are in free fall without a parachute and we're falling towards the Earth, at a certain point we're going to reach this terminal velocity that we're not going to accelerate towards the Earth any longer, and air resistance is going to kind of balance it out. So we're accelerating, or we're actually not accelerating any longer, and our velocity is moving the same. We also experience terminal velocity in this parachute example. At a certain point, this parachuter is not going to accelerate anymore, so we're at a terminal velocity where downward force is equal to the upward force. So it's just a constant velocity in that case. Also, an interesting thing to point out is that astronauts in orbit are in free fall. And actually, I'll talk about this on our last slide today, but astronauts are in this free fall. I want to talk about projectile motion first, and then it'll kind of make sense how they don't fall to Earth if they're in free fall. Alright, so projectile motion. Why does a projectile follow a curved path? And I'll just put out there that this projectile motion slide is a very basic introduction. If you move on to take physics, you'll be exploring this topic of projectile motion in more detail. So projectile motion is going to have two components. We've got a horizontal component and a vertical component. And when these two motions are combined, they form this curved path. So to define projectile motion, the curved path that an object follows when thrown, launched, or otherwise projected near the surface of Earth is what we call projectile motion. So if you were to throw an object, well, let me go to this slide first. We have projectile motion having a horizontal component. So when you throw a ball, there's no horizontal forces acting on that ball any longer, as long as we ignore air resistance. So the horizontal component of the velocity is constant after the ball leaves your hand. So we've got this, let me go ahead and throw this other description up here. So we've got this object, this ball that we threw, and it's got this horizontal component. So it's going to be constantly going this direction because of this horizontal component. Projectile motion also has a vertical component, which is going to be straight down as well. So when we throw the ball, gravity is going to pull it towards the Earth. It's going to pull it downward, which then gives the ball vertical motion. So again, in the absence of air resistance, gravity on Earth pulls the object that are in projectile motion downward. The value of this, and this value can be calculated, 9.8 meters per second squared, and it pulls this object as long as you're close enough to Earth at the same acceleration all the time. So when we've got this horizontal component and this vertical component interacting, we end up getting this curved path down to the Earth, basically. So if we're target practicing or shooting, we don't have to worry about this bullet going on forever, because we've got the force of gravity pulling down on that object that's going to bring it to the ground. So we've got that horizontal vertical component that's going to take place in actual problems. So orbiting, and the reason why our astronauts don't fall to Earth, is a form of projectile motion as well. So we've got the shuttle, or the astronauts in the shuttle. They're moving forward at a constant speed, and this path would be straight if Earth did not exert this gravitational pull. So the shuttle tends to want to go straight horizontal this way, but the Earth's wanting the shuttle to be pulled back towards Earth. So the shuttle's in free fall because gravity is pulling it towards Earth, and its path would be straight down if it weren't traveling forward. So the combination of these forces is going to cause us to have cause these astronauts to have this curved path. So the forward motion combined with free fall follows this curvature of the Earth. So they get high enough into the orbit to where they can go horizontally in one direction with free fall pulling them down, so that they can just keep orbiting the Earth. So, thanks for listening.